In this video, we are going to see the first application of the operational amplifier, which is called the inverting amplifier circuit. The inverting amplifier circuit, we connect our source, our input source, to a resistance Vs, to a resistance Rs, and then to the inverting terminal. That's why they call it inverting amplifier. And then we connect the non-inverting input to ground. Then there is a feedback resistor Rf that feeds the output voltage to the inverting input of the amplifier. So we have a feedback resistor Rf, we have an input resistance Rs connected to the source. Okay, in addition to the DC supplies. As you see here in this circuit, we'll assume idle op-amp. In order to assume, or if we assume idle op-amp, then we have two important assumptions. We have that Vp equals Vn. This is if we assume linear region, and this is always what we'll assume in the beginning. We'll assume linear region because otherwise the amplifier or the op-amp will not be amplifying. It will not be working as an amplifier if it is not in the linear region. So we'll assume linear region where Vp equals Vn. The second assumption is Ip equals In equals 0. So here Vp equals 0. Which means that Vn also will be 0. The voltage of this point is 0, right? Furthermore, the current going here and the current going here, In equals 0 and Ip equals 0. So here we assume, we analyze this circuit under the assumption that the op-amp is ideal and it is working in the linear region. So we have two assumptions, Vp and Vn. They are equal, and since Vp is connected to the ground, then Vn equals to 0, and the currents In and Ip, both of them are 0. Let's assume the current in Rs. We'll assume that the current in Rs is called Is, and the current in Rf in this direction is called If. Of course, Is equals what? Is equals the voltage of this point minus the voltage of this point over Rs. So Is equals Vs minus the voltage of this point, which we said it's 0. Is equals Vs minus Vn over Rs. So it's Vs over Rs. What about If, the current in the feedback resistor? The current in the feedback resistor equals the voltage of this point, which is V output, minus the voltage of this point, which is Vn. V out minus Vn over Rf, right? And Vn is 0, then it is equal to V out over Rf. Okay, now let's look at Cursive Current Law at this point, Is. Cursive Current Law at this point says that the summation of all the currents at this point entering this point is 0, right? So Is plus If minus In. Why minus In? Because it's leaving, In is leaving the node, equals 0. But anyways, In is 0. This gives us that Is plus If equals 0, or Is equals minus If, right? Because In is 0, there is no current here, then Is will be equal to minus If. Now, Is is equal to minus If, so we can write Is is Vs over Rs and equals to negative If is V output over Rf. From this equation, we can calculate that the output will be equal to negative Rf over Rs multiplied by Vs. And this is the famous equation for the inverting amplifier. So for the inverting amplifier circuit, the output is negative Rf over Rs multiplied by the source voltage. Rf is the feedback resistor, Rs is the input resistance with the source. You can call them, or in some other textbooks or some other problems, the name will not be Rf and Rs, right? But you have to understand that the feedback resistor divided by the input resistance. So output equals negative the feedback resistance, whatever you call it, Rf, you call it Ry, you call it anything, it's negative the feedback resistor divided by the input resistance connected to the source. Okay? Here we call it Rf and Rs, it can be called anything later. So this is a very famous equation for very famous application called the inverting amplifier. You can choose RF and RS, whatever you want. If you choose RF to be 10 kilo and RS 1 kilo, then you are going to amplify the input by a factor 10. If you choose this to be 100 kilo and this is 1 kilo, you are going to amplify the input by a factor 100. And there is a negative sign. This negative sign means what? What does it mean, the negative? Negative means you flip the signal. Flip the signal, you change the direction of the signal. So if you have a sine wave, for example, if you have a sine wave that looks like this, you will amplify it and flip it. So it will change the phase. Instead of having positive, it will be negative. Okay? So the negative sign here means phase change, phase of 180-degree change. Okay? Or basically you flip the signal. So you amplify and flip. That's why they call it inverting amplifier, because it inverts the signal and it amplifies it. Here the gain that we calculated, here between V output and V input, this is, we don't call it A, because A is the open loop gain. But this gain is called G, the closed loop gain. The closed loop gain. Okay? So here, the gain between V output and Vs, this is called G, and this is what we talked about before. This is called the closed loop gain, and it is equal to minus RF over RS. Of course, this analysis again is based on ideal op-amp, based on assuming linear region. If you solve this, and after you solve, you find that V output is higher than VCC or lower than negative VCC, then your assumption is wrong, and you say the op-amp will saturate either at VCC or negative VCC, as we will see in the example next. In this example, we have this inverting amplifier, okay, and it says assume that the op-amp is ideal. Good. Calculate V output for the following values of Vs: 0.4, 2, 3.5, many values. Okay. Specify the range for Vs required to avoid amplifier saturation. So let's start with the easy one. Calculate V output. Then we'll assume linearity. If we assume linearity, then we can use this equation. V output, assume linear region. Then V output equals minus the feedback resistance. This is the feedback resistance, minus 80 kilo divided by RS, which is the input resistance, 16, multiplied by Vs. So basically minus 5 Vs. So V output equals minus 5 Vs if you assume linear region. Okay, so now let's substitute Vs. Let's make a table. Let's make a table. Vs, V output. For Vs equals 0.4, V output will be minus 5 multiplied by 0.4. It will be minus 2. Minus 2 is in the range between the negative DC supply and the positive DC supply, so there is no problem. Next, Vs is 2. V output will be minus 5 multiplied by 2. It's minus 10. Again, minus 10 is within the range of the negative DC supply and the positive DC supply. There is no problem. When Vs is 3.5, V output will be minus 5 multiplied by 3.5. This is negative 17.5. Is it possible to have negative 17.5? No, because the output cannot go below negative 15, right? In this case, we say this answer is wrong. Our assumption is wrong, and the output is going to saturate at negative 15, because it will try to go to negative 17.5, but once it reaches negative 15, it will saturate, it will stop. So here we say that the answer is negative 15. Let's go. When Vs is negative 0.6, then V output will be negative 5 multiplied by negative 0.6, it will be 3. There is no problem with the 3 because it's in the range. When it's negative 1.6, then the output will be negative 5 multiplied by negative 1.6, it will be 8. Again, there is no problem with the 8 because it's within the range. Finally, if Vs is negative 2.4, then the output, if we calculate the output negative 5 multiplied by negative 2.4, it will be 12. But 12 is higher than 10. And we said that V output cannot go above 10, right? So here we say that this answer is wrong, and V output is going to saturate, the amplifier is going to saturate at 10, and that's it. This is for the first part. Then in the next part it says, specify the range for Vs required to avoid amplifier saturation. Okay, then in order to avoid amplifier saturation, ya shabab, what's the condition? Write the condition. Ask yourself, what's the condition for the amplifier not to saturate? Is that V output must be less than the positive DC bias, which is 10, and greater than the negative DC bias, which is negative 15, right? To avoid amplifier saturation. Right, what is V output? V output is negative 5 Vs. Then from here we can calculate Vs. If you divide over negative 5, then the signs are going to reverse. This will be negative 2 and this will be 3. So Vs must be in the range between negative 2 and 3. And of course here, if we increase above 3, there will be saturation. If we go below negative 2, there will be saturation. So in order to calculate the range at which the amplifier is not going to saturate, you have to write that the output must be between the positive DC supply and the negative DC supply. This is a very important condition to check for your assumption of linearity. Okay? We'll stop here in this video. Next video will talk about some practical effect, which is the effect assuming that the open loop gain of the op-amp is not infinity. So far we assumed the ideal op-amp with gain infinity. What if the gain was not infinity? We'll see the effect as only one slide. We'll see how this will affect our gains, our analysis in the next video, inshallah.